Doc here, the physics of sound and music, critical thinking with open pipe harmonics. Suppose we have memorized our silver bullet review sheet, which is not hard to memorize this table because there's a pattern. In other words, for the fundamental wavelength, or the first harmonic, we have 2L, where L is the length of the open pipe. Then to get the next one, we divide by 2. To get the third one, we divide by 3. To get the fourth one, we divide by 4, and so on. For the frequencies, we have the first frequency is F, the next one is 2F, the third one's 3F, 4F, and 5F, etc. Can we apply this, though, on an exam? So to help you here in this coaching session, we're going to generate a table with numbers, and then, like Jeopardy, when we have the answers, we'll come up with some questions. So what I have chosen here is a length of 30 centimeters for my open pipe length, and then using the formula here, the first harmonic wavelength is 2L, and then I'm going to divide by the number of the harmonic. So 2 times L is 60, 2 times 30 is 60, and then this is my 2L. So I divide by 2 to get the second one. 2 into 60 is 30. I divide the first one by 3 to get the third one. So 3 into 60 is 20. I divide the first one by 4 to get this one here. So 4 into 60 is 15. You can think of 60, divide it in half twice. You divide it in half once, you get 30. And if you divide it in half again, you get 15. And then to get the fifth case, I would divide the first one by 5. 5 into 60 is 12. And let's go one more and divide the first case by 6 and get 10 centimeters. What about the frequencies? Well, I have to worry a little bit about that because since it's not a string, I can't pick the speed to be anything. Wave speed, I have air, so I'm a little bit restricted here. Sometimes on exams I make up strange gases. But here I'm going to go to a hot room so that the speed of sound is 360 meters per second instead of 340. So the room temperature speed is 340 meters per second, and here we're going to go to a hot room where the speed is 360 meters per second. Now be careful, I have centimeters here, so let's get the speed in centimeters. 1 meter is equal to 100 centimeters, so I put 2 more zeros on the end here to get 36,000, and that gives me centimeters per second. Doing that gives me a realistic fundamental frequency, because if I have the wavelength and I have air, hot air with the speed being given, I am now forced to a conclusion as to what my fundamental frequency should be. In other words, 36,000 must equal 60 times F. So I can do that by dividing 60 into 36,000. 1 0 will cancel, and it will be like dividing 6 into 3,600. Well, 6 into 36 is 6, and the 2 zeros will simply ride along, so it'll be 600. So that's a realistic problem with no contradictions. Now, the chart over here tells me to get all the harmonics as I go up. I simply double, triple, quadruple, etc. So if I double and triple and go on, this will work out fairly easily because I am careful here, best I can, to pick numbers that work with the multiplication table, 12 by 12. So here 1 times 6 is 6, 2 times 6 is 12, 3 times 6 is 18, 4 times 6 is 24, 5 times 6 is 30, and 6 times 6 is 36. So therefore these numbers will appear here with 2 zeros tacked on in each case. So 2 times 6 is 12, the 2 zeros tacked on. 3 times 6 is 18, the 2 zeros tacked on. 4 times 6 is 24, the 2 zeros tacked on. 5 times 6 is 30 with the 2 zeros tacked on, and 6 times 6 is 36 with the 2 zeros tacked on. Notice that when the frequency goes up, the wavelength must go down. So these numbers increase, these decrease, so that the product is always the same. Let's check some of these to make sure the products are indeed the same. Well, 60 times 600, you multiply 6 times 6 and get 36, and there's 3 zeros tacked on. That's 36,000 centimeters per second. How about this last one? 10 times 3,600. Well, that would be 36,000. That would also be the speed of sound in the hot room. If you take a corresponding wavelength and frequency and multiply them together, you must get the constant velocity, which depends on the property of the atmosphere. See, the temperatures and the pressures. So let's do a couple more. 30 times 1200. 3 times 12 is 36, and you have 3 zeros tacked on, 36,000. This one here, 2 times 18 is 36, with the 3 zeros tacked on, 36,000. 15 times 24, that one's going to be hard to do, but I'm just showing you here how these will work. That would work if you took the patience to work it out, but look at this one here, 12 times 3,000 is 36,000. So nice relationship to note. Well, what about some questions here? Now that we have this nice chart with all the numbers, let's see if we can ask some questions. Well, here's a question that's not too hard, but I'm going to lead up to harder ones as we go, as I coach you here for the exam. Suppose I give you the fundamental frequency as 600 hertz, and I ask you for the third harmonic. Well, you have memorized your chart here, which is not hard to memorize since you simply put the harmonics here in front, 1, 2, 3, 4, 5, 6 on up. So if you want the third one for the frequency, you simply triple 3 times F, so 3 times 600, 3 times 6 is 18, and the 2 zeros tag along here, so that's 1800. Now suppose we ask the question backwards. We say that the third harmonic has frequency 1800 hertz. What is the fundamental frequency? Well, since we multiply by 3 to go up, we must divide by 3 to undo it, to go back. So 3 into 18 is 6, the 2 zeros tag along, and we get then the 600 hertz. Well, here's now a very advanced question. This is an A question. Suppose I give you the 1800 hertz and ask you for the frequency of the second harmonic. I'm giving you 1800 hertz as the third harmonic. The third harmonic frequency is 1800 hertz. What is the second harmonic? Well, you can easily get confused with ratios here, but it's easier to simply break this problem up into two problems. You simplify, say, I will reference this back to the fundamental like I did earlier by dividing by 3 to get my 600. The previous question did that. And then to get the second harmonic, I just double to get the 1200 hertz. So reference to the first harmonic and then go up is the easiest way to do this. And then the hard problem doesn't appear to be hard any longer. What about playing this game with the wavelengths? Well, we can give you the fundamental wavelength at 60 centimeters and ask for the third harmonic wavelength, and the chart here says that the third harmonic wavelength is 1/3 of the first. See, here you take 1/2 of the first, 1/3 of the first, 1/4 of the first, 1/5 of the first to do your wavelengths, because your wavelengths get shorter and shorter. So if we take 1/3 of the first, we get 20 centimeters. Always remember that the longest wavelength is your fundamental, and as you go up in the harmonics, the wavelengths get smaller and smaller, just like when we shook the spring in class, or that string. The model for the string is that spring I brought to class. When we shake that, we get smaller and smaller wavelengths, but the frequency goes up. And that's because the product, say, of the wavelength times the frequency must be the same. So if one goes up, the other must go down in value. So always remember that, and that's a sort of a common sense check that if I ask you for the third, given the first wavelength, it better be smaller. Now suppose we ask this question in reverse, and we give you 20 centimeters for the wavelength of the third harmonic. What is the first harmonic wavelength? Well, to undo that, you need to multiply, and here's where I see some students get confused by mixing up these columns. You have to be careful. If you're in the frequency column, you multiply by the harmonic number to go up in harmonics. And to undo that, you must divide. Here, to go up in the harmonics, you divide by the harmonic number. Say here's 6, the first one divided by 6, and then to undo that, you have to multiply. So to undo this, to go back to the first, since we divided to go up there, we must multiply to go back. So 3 times 20 is 60. And we go back to the fundamental. Now suppose we ask for the second harmonic wavelength if we're given the third. Well, always reference things back to the fundamental. So 20 times 3 to go back to the fundamental, and then divide by 2 to get the second harmonic. Remember, if you're given the length of the pipe instead of the wavelength, remember to always double that wavelength when you deal with an open pipe to get your fundamental and then go from there. What about if you're given this open pipe without this designation over on the left, and you're given that this length is 30 centimeters? What is the wavelength? Well, one way to do it is to recognize that one vertical line is the first harmonic, 2 vertical lines is the second, 3 is the third, 4 is the fourth. So you see the 2 vertical lines, you say that's the second harmonic. And if that's the second harmonic, then I use my wavelength formula for the second harmonic, which is 2L over 2. And 2L over 2 is simply L, and that means the answer will be the length of the pipe, 30 centimeters. Now, another way to do this is to play around with the nodes and antinodes. Whenever you go from a dash to an adjacent vertical line, they always alternate, that's 1/4 of a wavelength. So here is 1/4 of a wavelength, plus another quarter is 2 quarters, 3 quarters and 4 quarters. 4 quarters is a whole, that's a whole wavelength, and since that length is 30, the answer will be 30 centimeters. Suppose we're given this picture without the designation. Well, we can count the vertical lines, 1, 2, 3, 4, and say that's the 4th harmonic. And if that's the 4th harmonic, then the formula says take 2L and divide by 4. 2L divided by 4, 2 over 4 is 1/2. It's 1/2 of L. It's 1/2 of 30. The answer is 15 centimeters. The other way to do it is by counting the quarter wavelengths. 1/4, 1/4, that's 2 quarters, 3 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, 8 quarters. 8 quarters, that's 8 divided by 4, that's 2 holes. 2 holes have to be fitted in this length of 30, so that means 1 hole must be 15. And we get the answer again, 15 centimeters. So play around with this. Also, by the way, the nodes here, if this doesn't move, that's a displacement node. This moves here, that's a displacement antinode. But for the pressure, remember, you reverse it. So this is a pressure antinode where the pressure increases and decreases, and this is a pressure node where the pressure is atmospheric pressure. There's no change in the pressure.